Okay, this is the last topic we need to cover before the exam, and it's enamines. And essentially, if you take a ketone or even an aldehyde with a secondary amine, what you can do is you can end up forming an enamine. Now, an enamine is different from an imine. The mechanism of this reaction is the electrons add to this, and so the mechanism is very similar to that of imine formation. And then that OH gets protonated. So far, the mechanism is just like imine formation. Protonate the OH to make it into a good leaving group. And then have the neutral nitrogen swing its electrons down and kick off the water. Now, in imine formation, you have a hydrogen attached to the positive nitrogen that you're going to deprotonate to form the imine. But in this case right here, we don't have a hydrogen off that nitrogen to deprotonate. Instead, what we have is an enolizable hydrogen, a hydrogen alpha to the double bond N, alpha to the iminium. And so what happens instead is your secondary amine comes in and deprotonates that. And you get your enamine. Now, enamine, this enamine formation reaction, it's a reversible reaction. So if you have an enamine and add water to this reaction, the reverse occurs. You end up with a carbonyl and an amine. And enamines typically are unstable in water, and they become a carbonyl and an amine. You can think of enamines as the nitrogen version of enols. Enamines are nucleophilic due to this resonance structure. And in terms of enamines in synthesis, prolidine is often used to make enamines. And synthesis reactions. So, what you can do with these reactions is, say we have a ketone. We can treat it with our secondary amine. That is our enamine. And then from this enamine, we can react this with varying electrophiles, such as the ones that are typically used are things like acid chlorides, Michael acceptors, or SN2 electrophiles. Although this lattice one comes with some restrictions, either must be an sp2 carbon or a hydrogen in order for the reaction to work. And then each of these, when you expose them to water, the enamine is replaced with a carbonyl. Okay. Now, you might notice something about the enamines intermediates. The double bond. Here, the double bond is between these two carbons. In the other two cases, it's away from that. That has to do with the mechanism of the reactions. And we'll get to that in just a moment. First, I need to talk about how these reactions are synthetically done. So typically what happens is you have your round bottom flask and you throw in your ketone and your amine and you heat it up and you distill out water, and then you have basically this in some solvent, and you always have a little bit of leftover amine. And then you never truly isolate the enamine. What you do is then you add in your electrophile, or your Michael acceptor, or your acid chloride to this. and let it do its reaction. And then you throw in water and purify your compound and try to isolate it the best you can. Okay. So what I'm trying to get at is this compound right here isn't isolated before adding in your electrophile to it. Okay. That's important. Now, let's talk about why the double bond appears in the different places. That has to do with the mechanism. So once you have your enamine, and let's do the acid chloride reaction first. You throw in your acid chloride, and it does the acid chloride reaction. Basically just an SN2 reaction, displaces the chloride. And you get this species right here, the aminium. Very similar to this aminium right here, which a base came and deprotonate to form the enamine. And we have the same situation right here. We have, though, two different hydrogens that you can pull off to reform the enamine. The blue hydrogen is considerably more acidic because it's between two electron withdrawing groups, making it the more likely candidate to be deprotonated. Like so. Now, in terms of the other reactions, say the Michael acceptor, and then as a proton source, you have this ammonium come around that can take the proton. You now have your aminium. Here, the blue hydrogen and the red hydrogen both H's have near equal acidity, as opposed to up above, the blue hydrogen is much more acidic. So in this case right here, the red hydrogen is preferred to be the one taken off. of that. The reason why. Well, so if we take the blue hydrogen off, we get this compound. If we take the red hydrogen off, we get this compound. It turns out this compound right here is more stable because this carbon here is sp3. Why that makes a difference is because this shouldn't be a line. It's actually more like either a wedge or a dash. It's out of the plane. This, on the other hand, is sp2. What that means is that all of these atoms are in the plane with each other. And what you end up getting is you start to get steric clashes between these. As opposed to here, these atoms are not in the same plane. And since they're not in the same plane, the hydrogens aren't in the same plane either, and as a result, there's more space for them, and you don't get the steric clashes, as opposed to here, where they are all in the same plane. On the other side of things, what the atoms that are in the same plane are these hydrogens. That hydrogen. And as a result, the steric clashes are minimized by that. In the example of the dicarbonyl, or I should say the carbonyl side, you have the steric clashes. But the extra resonance stabilization makes up for it. Okay. Now, that's the same reason why the SN2 reaction, puts a double bond the same way. It's to alleviate that strain. Now the requirement that R equals a hydrogen or sp2 carbon. This is empirical, meaning they've done a lot of reactions and they found that it works best when the R group is a hydrogen or sp2 carbon. What that means is the R group is a hydrogen. Achieve this with methyl bromide or methyl iodide. Get that. Or say it's an sp2 carbon, like so. If it's an sp3 carbon, you start to get some side reactions. And you start to get a lot more nitrogen alkylation. And this is purely empirical. Like so. Okay. Now, real quick, the mechanism for enamine hydrolysis. Well, enamines, slightly basic. So what happens is you can protonate the enamine with water. And then have water attack. You can have water attack, or you formed OH minus in this last step. You can have OH minus attack, either one. Amines are slightly basic, so you can protonate the amine with water. base takes the hydrogen off the O. Get an O minus. And the O minus swings down, kicks the amine off. Okay. Now, not all enamines are unstable to water. This is an example of an enamine that is completely stable to water. This ring, the smallest of these rings is this one right here. It's called a pearl ring, and it's aromatic. Another pearl that's actually quite famous, although it's a little complicated. Let me make sure I draw this correctly. Like so. And then this has a carbonyl, a nitrogen, phenyl group on it. And this has a phenyl group right here. And this also has phenyl group. Oops, 2 carbons. Okay, this fancy molecule right here is called atorvastatin. It's a type of drug called a statin drug. It's sold under the brand name of Lipitor. And it's essentially a billion-dollar drug. Highly lucrative drug. Used to control basically cardiovascular disease. Now, where a lot of pearls come from is a reaction called the Paul-Knorr pearl synthesis. And typically, all you need is an amine, and a 1,4-diketone. And you heat it up, and get this. And essentially, what's happening is you make an enamine on one side, and then you use the NH of the enamine on the one side to make an enamine on the other side as well. It's just two enamine synthesis reactions. You might recognize that the 1,4-diketone used in the synthesis. Well, that can be made by the Stetter reaction. The Michael acceptor. Well, that can be made by an aldol reaction. So on and so forth. And so what you're able to do is make some pretty useful molecules by these simple reactions that we've just been talking about. And that's sort of the power of these reactions. This one right here can be broken down into some very simple fragments, a very complex molecule. Okay. That's pretty much it. I'm not gonna, this mechanism right here, all it is just two enamine formations. And that's it. So, that's all the reactions that are possible on this next coming exam. And I hope to have some practice exams up soon.